Professor, good morning everyone. I'm Filippo, the chairman of Group M, and this is our third and last project, Engine Belt Vibrations. I would like to say thank you to all my group mates for their big effort in this project. Today we are going to see a quick introduction of the problem, then the theory and the numerical implementation parts, at the end the results and the conclusions. There are many types of belts. There are the flat belts, the V belts, the multi-grooved ones and the timing ones. In the automotive field, just the multi-grooved and the timing ones are used. The belts are made of rubber and nylon. Rubber is used to have a high friction coefficient to avoid slips, and nylon is used to have a big enough tensile strength to withstand high loads. But we will focus on vibrations. Vibrations are caused by the centrifugal forces, the preload that are applied to the belt, the variation of the axial speed of the belt. The consequences can be that the behavior of the belt and its reliability are affected, and the belt deflects from the longitudinal axis as it vibrates. The problems can be the risk of resonance and instability when it reaches the critical axial speed. We modeled our system as a traveling Euler beam with simple supports. In addition, we neglected the tension fluctuation, the pulley eccentricity, and the nonlinear strain, which is due to small longitudinal displacement. In the first case, we have to consider a simple moving beam. We want to analyze the free vibrations of the beam. We found the equation of motion, first going through the Newtonian approach. In the equation we can see the inertia force, the axial tension, and the last component is due to the bending stiffness of the belt. Then we consider the boundary conditions of a simple supported beam. It is also useful to go on a non-dimensional problem, and at the end we ended up into the last equation, which is the equation of motion. To simplify the solution of the problem, we used an approximated method, the Galerki method. The displacement is expanded in a series of suitable trial functions from 1 to n, where n is equal to 8. As trial functions, we chose the ones of the static problem, which are the sign functions, and they must respect the boundary conditions. We substituted the displacement field into the equation of motion, and then after applying the projection on the trial function, we obtained n uncoupled ordinary differential equations, both in the standard and in the compact form, where C is the damping matrix and K is the stiffness matrix. In order to solve the problem, we rewrote the equations in a state form. And going through the eigenvalue problem, we obtained 8 couples of complex and conjugated eigenvalues that gave us the natural frequencies, and 8 couples of complex conjugated eigenvectors. We can notice that for high speed, the natural frequencies drop to 0. These speeds are called critical speeds. From these critical speeds, instability occurs and multiple equilibrium positions are possible. Here we are now switching to the numerical implementation section. For the modes of vibration, we implemented 3 different plots to evidence all the different features, and you are going to see them in few minutes. For the first plot, we show the imaginary and real part of eigenfunction, which is defined by the trial function times the relative component of the eigenvector. Then, to evidence the weight of each trial function on the single mode shape, we made a bar chart in which the height of each chart is the value of the eigenvector component. The third and last plot is a dynamic representation in which the time-dependent coefficients have been found using the ODE45 function. In the second case, we were requested to analyze the response of the moving beam to a hammering force in the midspan of the belt. The hammering force is modeled as a half-sine function, where L here is the length of the belt span, F0 is the amplitude of the hammering force, T is the period of sine, delta here is the Dirac delta function, and we have also H, which is the Heaviside function. It's trivial that the hammering force is like an impulse. So, as we can see from its spectrum here, it stimulates all the modes. Converting it into a dimensionless problem and applying the Galerki method, as we did before, we obtain the extant force and the equation of motion. We also rewrote the equation of motion in a state form. Before switching to the results section, here we can see some data. Okay, we are at the results section. In the graph on the left, we can see the real and the imaginary parts of eigenvalues. The imaginary parts become 0 in correspondence of the critical velocities, while real parts are 0 before the critical speeds, and they become different from 0 after them. To double check our result, we also plotted these vertical lines, the black lines, in correspondence of the critical speeds using the analytic formulation. On the right, we have the bifurcation diagram. Instability occurs after the first critical speed, which is at 13,500 rpm. It's a value that cannot be reached during the normal working of the engine. Analyzing the mode shapes, it is possible to see in the bar chart that for low axial velocities, so at 10% of the critical speed, each mode is mainly represented by one single trial function. They are in red color. While increasing the axial velocities, so at 90% of the critical speed, the weights of the trial functions on the single mode are more and more distributed. They are in blue color. We can see it here, 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 everywhere. They are distributed. We'll now talk about the representation of imaginary and real part of eigenfunction. In accordance with what we discussed before, the imaginary component of the shape grows as the speed increases, and the main effect of velocity is observed in particular for high modes. To evidence the fact that we have traveling and not standing waves, we show you a dynamic representation of the first mode. As you can see, the nodes are not present. We are now seeing the result of the second case. Here we have the transient response at 1000 rpm. And here the transient response at 10,000 rpm. So, As we can see, at high axial speed, the belt is more unstable, so the amplitude of the response is higher. In conclusion, we used the Euler beam, then we applied the Galerki method, we went through the eigenvalue problem to find the natural frequencies and the critical speeds. In particular, we saw that the first critical speed was higher than the maximum RPM of an engine. Then we obtained the mode shapes and we find out that at low speed each mode is represented by a single trial function, while at high speed they are more distributed. Finally, we analyzed the first problem and we discover that at high speed the displacement of the belt increases. Now the project is over, but we decided to go deeper in the problem. We have some extra. We repeated all the tests with a lower tension, reducing the engine power by 40%. Here we can see the response of the same excitant force at 1000 RPM. And here at 10,000 RPM. So, in conclusion, we can say that the deformation of the belt increases. In fact, with the 60% of the belt tensioner, the amplitude of oscillation is twice higher at 1000 RPM and 3 times higher at 10,000 RPM. In addition, we saw that the critical speeds decrease, and this may become a problem for example, the small engines, like motorcycle engines, because they reach high RPM, which may overcome this limit. The solution to this problem could be a through pulley located in the midspan. It will decrease the length of the beam and the amplitude of the oscillation as well. Thanks for your attention.